In our last lecture, we were looking at, or just began talking about reaction rates, again, relative to the fact that if a reaction can go over the activation energy barrier in one direction, it may well be able to go over the reaction barrier or activation energy in the other direction. And again, using our basic reaction A plus B to produce product C, we said that initially here, if we were to take a container and we were to put some A particles in here and some B particles, we could get some A-B collisions that would occur. And if the A-B collision occurred with at least the activation energy, then it could become product C. Well, after some length of time then, as the system begins to operate, of course, we're going to form some C's, so we'll stick some C's in there. And it would not be unlikely that occasionally we're going to get a C colliding with a C. And when that happens, of course, we might get what we call the reverse reaction. In other words, the C's now breaking apart once again to reform product or the reactants A and B. Because again, if we looked at the activation diagram for this, and so we're starting with our A and B, we have some activation energy barrier, and we get C. This is representative then of what we would call an exothermic reaction, energy being given off. And so if we have enough energy in the system for A and B to get over the hill, then in that same system, we may well have enough energy for when two C's collide for them to likewise get over that energy barrier. So we talked about then that we really have two possible reactions occurring here. We have a forward reaction, which involves A and B colliding with each other, and we draw this arrow, so we'll call that the forward. And of course, the forward reaction in this case is dependent upon or proportional to, we would say, the concentration of A and the concentration of the B particles. We saw in the previous chapter that, of course, one of the factors controlling the rate of a chemical reaction is, in fact, the concentration, which affects the number of collisions. And so we have then a description of defining the rate of this forward reaction. But then we also have the possibility, as we said, of this reaction happening, which is the reverse reaction now, so we'll just put a letter R there for it for reverse. And the reverse reaction then is going to be proportional to the concentration of the C particles. Because as we have C particles being formed, there is more and more probability of having a C-C particle collision, and therefore a greater chance of the reaction proceeding in the reverse direction. Let's then, still using the same equation, let's change our description now from a proportionality to an equality. And we did this when we looked at the ideal gas equation. We talked about the fact that we could change from pressure being proportional to N and R and T and V, all right? We said that we could make that an equality by putting in a proportionality constant K. In the case of the gases, of course, we replace that K with a letter R, but it's still a constant. So we can rewrite this now. The rate of the forward reaction is equal to, so now we're talking about an equality, not a proportionality, mathematically. It's equal to then a K, which we call a rate constant, and that is going to be a number that is specific for that particular chemical reaction. This is not a universal K like R was to the gaseous behavior. This K is very specific to a particular chemical process that's occurring. Well, we can do the same thing for the reverse reaction now, and we can say then the rate of the reverse reaction is equal to some rate constant K times the concentration of C. Now, if we were to take a look at these two rates of the reaction here, so we're going to look at the rate now, and the trying to get this on here right, there we go. If we look first of all at the forward rate and think about it for a second, keep in mind that we have a closed container. As the reaction proceeds to form C, what's happening to the concentration of A and B? Anyone? It decreases. We have to use A and B up to form C, right? I mean, we don't just spontaneously get C out of nothing. A and B particles are being used up to form the C, which tells us then that the rate of the forward reaction, if A and B are decreasing, what's going to happen to the rate? It's going to get slower, isn't it? If we have less A and B, we're going to have a slower rate. Now, in the reverse reaction, we started with an initial concentration of C of 0. There weren't any C particles in there. The C particles had to be formed by A and B reacting. So the initial rate of the reaction in the reverse direction, if concentration of C is 0, therefore, of course, obviously, the rate is 0. Now, this plot here is plotting rate, and this top line that we see down here is now going to represent the rate for the forward reaction. And you see this purple line down here, and that's going to represent the reverse reaction. So I'm going to slowly pull this across now, and we'll see what begins to happen. As we do so, we see that the forward rate, the red line, is dropping off because the concentration of A and B continues to decrease. And we see that the rate of the reverse reaction is continuing to increase now. It's coming up, it's increasing, because the concentration of C is increasing as A and B is used up. Well, this continues on for some length of time, and we see that the forward rate keeps getting smaller, the reverse rate keeps getting larger, and finally we reach a point then at which now the forward rate and the reverse rate have become equal. In other words, we are now producing C at the rate equal to that we are using up the C. And we refer to this, where these two rates then have become equal, we refer to this then as the equilibrium for the reaction. The reverse rate and the forward rate have become equal, and we're now at equilibrium. Now, we've talked about equilibrium before. We talked about equilibrium when we talked about dissolving. We said that a substance dissolves, but finally we reach a point where the rate at which it precipitates, goes back to the solid form, becomes equal to the rate that it's dissolving, and we have a saturated solution. We have an equilibrium solution. We also talked about, above liquids, we talked about liquid vapor pressure. Molecules escaping from the liquid in a closed container. And finally, of course, some molecules now begin to stick back to the liquid or condense. And we said when the rate of evaporation became equal to the rate of condensation, we have an equilibrium. And we talked about the equilibrium vapor pressure. of a liquid. And here we're talking now about an equilibrium again. Two opposing processes have become equal, and we've reached equilibrium. And as in the previous two equilibriums that we talked about, this is a dynamic equilibrium. By that we mean that at any instant in time, if we could stop and freeze the system, the same particles are not necessarily in the same form. In other words, some of the particles that used to be A and B's have become C, and some of the particles that were C's have gone back to being A and B. So there's a constant process going on, a dynamic process going on. But as far as the concentrations, once equilibrium has been reached, we wouldn't notice any change in concentration. If one of these species were colored, for instance, the solution would reach a maximum color, and that would be it. But it doesn't mean that the chemical reaction has stopped. It only means that the two processes have become equal. And so in chemical reactions, then, we can talk about this equilibrium. Now, this equilibrium is important to us from an industrial standpoint because, for instance, if I want to produce C here as my money product, if I want to produce C, I would like to, if at all possible, make sure that I get a lot of C before equilibrium is reached. And the question became, can one affect the rate of a chemical reaction? I should say it differently than that. Can one affect the conditions of a chemical reaction such that you can favor one side or the other at equilibrium? In other words, can we do something to a reaction to get a greater amount of C? Can we do something to a reaction to prevent C from being formed? That might be just as important to us. Well, a French chemist by the name of Le Chatelier studied a lot of chemical systems at equilibrium. In other words, he allowed a system to reach equilibrium, and then he subjected it to some changes in conditions and studied what effect those changes had. And Le Chatelier's principle then basically states that if we have a system which has reached equilibrium, now when we talk about system here, we're talking about a chemical reaction. If we have a system at equilibrium and subject it to a change, now that change could be a change in temperature, change in concentration, change in pressure, change in volume. We subject it to some particular change. Then Le Chatelier said the system will attempt to offset the applied change. Now, in other words, what Le Chatelier found was if I have a chemical reaction and it has reached equilibrium and I change the pressure on that system, the system would try to do just the opposite. It would try to get rid of that increase in pressure. It would try to decrease the pressure. If I lowered the temperature of a chemical reaction, it would try to increase its temperature back. It will try to do exactly opposite of whatever I do to the system. Now, it will attempt, however, there are many cases where we find that the system can do nothing about the change that we have applied, and therefore the equilibrium cannot be affected. But Le Chatelier was saying that if we subject a system to a change, and if the system can, it will try to offset that change. It will do the opposite thing. The best way to get a feel for Le Chatelier's principle is to look then at a particular chemical process or chemical reaction and make some predictions and see if we can understand what is occurring. Here now is a chemical reaction between gaseous water, solid carbon, energy in the form of heat, and our products are carbon dioxide gas and hydrogen gas. And we show equilibrium in a system by showing a double arrow. So when we write a double arrow in a chemical reaction, it indicates that the chemical reaction is in fact a reversible reaction, meaning that it can reach equilibrium. Now, this system has reached equilibrium, and now we're going to apply Le Chatelier's principle to make some predictions. The first is, let's suppose that we decrease the pressure on this reaction. What would that do to the equilibrium involved? In other words, will it now shift towards more products? Will it shift towards more reactants? Whatever the case. Now, if I decrease the pressure, the system will, if possible, try to increase the pressure. Now, we have to get a mental picture. This is a closed system. I mean, that system can't just grab molecules, can't do things like that. So it has to do something internally then to offset that change. Let's see if, again, maybe we can draw a little picture here. We have a closed system, and we have in it some H2O as a gas, we have some CO2 as a gas, and we have some hydrogen as a gas, and we had some carbon as a solid. Now, if I had this in a piston type system, what I'm saying is that I am going to then pull up on the piston. I'm therefore going to decrease the pressure inside. Now, if I decrease the pressure inside, again, Le Chatelier would predict that the system will try to increase the pressure inside. Now, the only way the system could increase the pressure inside here would be to do what? Produce a greater number of gaseous particles. It can't affect the temperature, it can't change its volume. The only thing it could do would be increase the number of gaseous particles. Well, let's go back to look at the equation once again. We see that on the reactant side we have how many gaseous molecules? How many gaseous molecules do we see on the reactant side? One. How many gaseous molecules do we see on the product side? Two. So therefore, if the equilibrium were to shift in this direction, it would double the number of gaseous particles in there. For every molecule of water that is shifted to this side, we lose one gaseous particle and produce two. So, if I decrease the applied pressure, okay, I've pulled up on the piston, and the system now would want to increase the pressure, it could do so by increasing the number of gaseous particles. And in order to increase the number of gaseous particles, it would have to shift toward the product side. So we would put an arrow pointing that equilibrium is going to shift by Le Chatelier's principle, to the right, or we might say toward the product. Okay? Well, you see, if I wanted to produce hydrogen gas from the reaction of water and carbon, then one way to increase the amount of hydrogen I would get out would be to operate it as a low a pressure as possible. If I operate at a high pressure, if I increase the pressure, the system is going to try to decrease it, and in order to decrease it, it would want to form less gaseous molecules. It means it would shift toward the reactant side. All right? Let's look at this one. Temperature is decreased. Now notice that in order for this reaction to become products, we have to be putting energy in. It's an endothermic process. So therefore, if I were to decrease the amount of energy available, the system will try to give me back that energy. If I start pulling energy out, it will give the energy back. The reaction in this direction is exothermic. It's endothermic as it's written from left to right, but it's exothermic as viewed from right to left, the reverse reaction. So the forward reaction is endothermic, and the reverse reaction is exothermic. So if I decrease the temperature, the system will try to increase the temperature. It'll try to put that heat energy back. And to put that heat energy back, it would have to go in the exothermic direction. So if I decrease this, the system is going to go this direction to try to give me that energy back. So it is going to move to the left or toward the reactant side. So in other words, again, if I wanted to produce hydrogen gas as a product, from an equilibrium standpoint, I would want to have the temperature as high as possible, because increasing this would shift equilibrium that direction, giving me a greater amount of carbon dioxide and water. All right? Now, let's jump C just a second. Let's go down to D here. Some hydrogen is removed. Some hydrogen is removed. In other words, back to my container here, if I somehow could put in some sort of a material that would attract hydrogen over here, so some of it is removed. Okay? So that's what we're saying. We're going to remove some of the hydrogen. Now, again, according to Le Chatelier, if I remove some hydrogen, if I decrease the hydrogen, the system will try to increase the hydrogen. Whatever I do, the system's going to try to do the opposite. Well, the only way it can increase the hydrogen would be for more water to react with carbon to form more hydrogen. So if I pull some of this out, then the system is going to shift in that direction to try to put it back. And so we're going to get a shift now to the right for that process, and or toward the product side. So in other words, if I pull some out, the system will shift. I will have a decrease in the amount of water now because some of it's going to be used up. I'll get an increase in the CO2, and I'll get an increase back in the hydrogen. It's going to try to replace that hydrogen that I removed. Now the last question here deals with a catalyst. A palladium catalyst is added. Now we know that a catalyst is a chemical that speeds up a chemical process, and it's ultimately regenerated in the final steps of the reaction. Catalyst is not used up in the process. It can be used over and over and over and over and over and over. A very small amount can catalyze a lot of a reaction. All right. The question is, if I add a catalyst, will this favor one side or the other? Well, if we go back to our energy diagram, we'll just draw it on here. If we look at an energy diagram once again, and this would be our reactants over here, in this case it would be the H2O and the carbon, but we'll just write H2O, and we have this barrier here, and we have our gaseous products, and I'll just put the hydrogen here. But if we put in a catalyst, what does a catalyst do? It lowers that activation energy barrier, right? It cuts this hill down in some fashion by providing a new pathway. But notice that if I in fact cut this hill down for this direction, whatever I've done to decrease the activation energy for this reaction, I have also decreased the activation energy for the reverse reaction by the same amount. And therefore, whatever I have done energy-wise to one process, I have done for the other process. And so, in fact, adding a catalyst to a system then has no effect on the equilibrium. Adding a catalyst does not affect the ratio of products to reactants that we get. Okay? So a catalyst does not affect equilibrium. Now, a catalyst affects how fast we get to equilibrium. But a catalyst doesn't affect at what point we reach equilibrium. In other words, how much of each of these is present is independent of whether we use a catalyst or not. It will be the same whether we use a catalyst or not. But the value of the catalyst is it allows us to get to that equilibrium quicker. And from an industrial standpoint, that's important, because if I'm putting energy in this process to produce a product, that costs me money. And so I would like to get the maximum amount of product in the minimum amount of time to make the maximum amount of dollars. It's pretty straightforward. And so as a chemist or a chemical engineer, then I would be looking for ways in which I can either get to equilibrium quicker or somehow shift the equilibrium to get a greater percent of my product produced within that length of time. So we can look at two things: affecting the rate of a reaction or affecting the equilibrium of the reaction to get a better yield of product. Well, let's look at another one here. This is another chemical equation: calcium sulfite, solid, reacting with sulfuric acid, solution, aqueous, and we get calcium sulfate, that's a 4 there, not a 9, aqueous, sulfur dioxide gas, liquid water, and energy. So this is an example now, of course, of, as it's written, at least an exothermic reaction. Energy is a product in this case. Now let's think what would happen to this system as we made certain changes. If we decrease the temperature, okay, so in other words, if I go over here now and decrease this one, I'm going to pull energy out, I'm going to cool it off. If I decrease the energy, lower the temperature, the system's going to try to increase that energy. It's going to try to put it back. It's going to try to raise the temperature back up. And in order to do that, it would have to do what? Shift toward. If I decrease it, the system will try to increase it. The only way it can increase it is to produce more products. So it's going to shift now to the right, producing a greater amount of products. So if I wanted to form sulfur dioxide gas by this process, the best way to do it would be do so at a low temperature. That's going to favor equilibrium going towards the product side. All right, volume is decreased. Volume is decreased. go back to look at a drawing here. So we have the system, the chemical reaction now with everything in here. So we've got calcium sulfate, solid. We've got the sulfuric acid. We've got calcium sulfate. We have some water. We also have, so we'll just put all of this down here as being this. And then we have some SO2 gas. Now, we're going to push down on the piston. And when I decrease the volume, now we go back to our gas laws. When I decrease the volume, what happens to the pressure? It increases, okay? Volume and pressure inversely proportional. So we said volume is decreased, therefore pressure is increased. Now, if the pressure is increased, the system should try to do what? We've increased the pressure, the system will try to decrease it. All right? Now, the only way the system can decrease the pressure is to decrease the number of gaseous particles. Well, all right, so we want to decrease. The only gaseous particle we had in the whole thing, in our whole equation, was SO2. And we want to decrease it because the pressure is increased. So let's go back and look at the chemical equation. In order to decrease the SO2, which way does the reaction have to go? Toward the reactants, right? It needs to go this way to use the SO2 up. If the SO2 and water in this react to form this, we'll decrease the SO2. So therefore, if volume is decreased, pressure is increased, the system will try to decrease the pressure. It'll shift to the side with the fewest number of gaseous particles. So it'll shift in this case to the left towards forming or keeping more reactants. Okay? Some calcium carbonate is removed. Whoops, I think I miswrote that. I think that maybe this should be calcium sulfite, because that's the only solid. And there's some calcium sulfite solid is removed. What will this do on the equilibrium? Again, if we think about our picture here, if we had a chunk of calcium sulfite down here, that's the solid, CaSO3 solid. Let's suppose that I removed half of it. Went in and I just picked out half of the solid that was in there. Is that going to affect the equilibrium? Well, the question is, by taking some of the solid out, did I change the concentration of the solid? No, because concentration of a solid is only dependent upon its density. And whether I have a little tiny chunk or a great big block in there doesn't make one bit of difference. It's the same concentration of calcium sulfite in there. So therefore, adding or removing a solid does not change concentration, and therefore, if we're not changing concentration of anything, we're obviously not changing the rate of anything. And so adding or removing a solid from a system at equilibrium does not affect the equilibrium. So this one then would have no effect. No effect. All right, let's look at this one. Some SO2 is removed. Now, if I pull some of this out, I could put something in that might absorb the SO2. If I take some of this out, if I decrease it, according to Le Chatelet's principle, if the system can, it would increase it. In order to increase the SO2, the only way we can get more SO2 in the system is for more reaction to occur. More of this has to be converted to that side to give us back the SO2. So therefore, we would predict that it's going to shift towards the right, or we would say toward the product side. We're going to get then more calcium sulfate formed and more water formed and more energy given out if we decrease the SO2, because the system, to put it back, has to form more of those other things as well. The last one here, pressure is decreased. Well, this is just the opposite of what we just said a moment ago when we talked about volume. Because if the pressure is decreased, then it means that in order to bring the pressure back, it would have to do what? Increase the number of gaseous particles. And which side has the greatest number of gaseous particles? The product side. Matter of fact, it's the only side that has a gaseous particle. And so if I decrease the pressure, in order for the system to increase the pressure, it would have to increase the number of gaseous particles, and so it is going to shift towards the right or towards the product side. So, Le Chatelier's principle basically again says that if we have a system at equilibrium, indicated usually by the double arrow, and if we subject that system to a change, whatever change, temperature, pressure, volume, concentration, the system will try to offset that change. Can't always do so. In the case of a solid, it can't change it. All right? Sometimes in the case of a pressure or volume, it couldn't change it. If we had the same number of gaseous molecules on both sides, if we had 2 molecules on the reactant and 2 on the product side, then changing pressure or volume can't change equilibrium. There wouldn't be any reason for it to shift one way or the other. If it forms 2 over here by using up 2 over here, that doesn't change the pressure or volume. If it uses up 2 over here and forms 2 over here, that doesn't change anything. So unless there's a difference in the number of gaseous particles on the 2 sides, then of course we wouldn't be able to get a change to occur. All right. Now, let's go back and look at this a little bit from a more quantitative standpoint. Le Chatelier's principle is strictly a qualitative. We're saying the system will change, but we're not saying anything about how much. We're not talking about it from a quantitative standpoint. At equilibrium, we said that the rate of the forward reaction has become equal to the rate of the reverse reaction. We also said that the rate of the forward reaction was equal to a rate constant times the concentration of A times the concentration of B for the particular chemical reaction we're looking at. And further, we said that the rate of the reverse reaction was equal to a rate constant times the concentration of C. So at equilibrium, these 2 things must be equal. And we have defined each of them relative to concentration of reactants and products. So now we could go ahead and plug those in, and so we can make the statement of this way. This here, rate constant forward times A times B, is this one. And the rate constant times C is the rate reverse. And at equilibrium, these 2 things have now become equivalent. Well, let's do just a little mathematical rearrangement here. Let's go ahead here and divide the Kf by Kr, and then let's divide the concentration of C by the concentration of A and B. And if we do that, then of course we get this relationship right here. This is just the algebraic now rearrangement of this. Kf divided by Kr and then I divided both sides by concentration of AB, so we have concentration of C over A and B. Now, this condition that we have just described only occurs at equilibrium. And further, a constant divided by a constant will give us a what? A constant. So if we're going to divide K by K, we're still going to have a constant. This time we're going to call it K, large K, and we'll call it EQ because this only occurred at equilibrium. And so this is defined as the equilibrium constant then for the system. This is defined as the equilibrium expression for the system. Now, in general, for equilibrium reactions, we can write in a general fashion that the equilibrium constant K is equal to, and this is an equality, so this is a numeric value that we're talking about. The equilibrium constant expression is equal to products concentration. That's what those little brackets mean, and we talked about that earlier in a chapter when we talked about pH, for instance. Brackets means moles per liter. Concentration of the products in moles per liter raised to the power X multiplied by the concentration of the reactants raised to the power Y, where X and Y are the coefficients from the balanced chemical equation. The coefficients from the balanced chemical equation. All right? So now we can go ahead and begin writing then equilibrium constant expressions for chemical reactions. And let's just take a look at doing a couple of these. Products over reactants raised to the power that they appear in the balanced chemical equation. The first one, we have the chemical reaction NO2 plus SO2 yields SO3 plus NO. And we want to write the equilibrium expression. So KEQ is going to be equal to the concentration of SO3 times the concentration of NO. Now, I don't put the power 1 down. If nothing is shown, it automatically implies that it's to the first power. Divided by concentration of NO2 times the concentration of SO2. Please note that these are products. These are multiplied, not added together. I'm not putting a multiplication sign between them. Just putting the brackets that way implies that they are multiplied times each other. Products over reactants. Equilibrium expression. Let's look at another one here. Here we have a reaction of phosphorus pentachloride with hydrogen to produce phosphorus trichloride and hydrogen chloride. So we're going to write KEQ. The equilibrium expression will be equal to the concentration of the PCl3 multiplied by the concentration of the HCl, quantity squared, all divided by concentration of PCl5 and the concentration of H2. So again, products over reactants, each raised to the power that they appear in the balanced stoichiometric equation. All right. Let's look at a third example here, writing an equilibrium expression. So we would write KEQ is equal to concentration of the S2 minus aqueous, concentration of H2O divided by concentration of HS minus and the OH minus. All of these are aqueous. I just didn't write it, except for water, which is a liquid. Now, seeing that this is a water system, water solution, aqueous implies that these are water solutions, the concentration of water itself can't be changed. And so this is in fact a constant in itself. The concentration of H2O. Dumping in more H2O doesn't change its concentration. Its concentration is dependent upon its density. And so it doesn't make any difference how much water we have as a liquid. Its concentration is always the same. So therefore, if this in fact is a constant, then why include it in the expression? It could be just incorporated over here. And so our first rule on writing equilibrium expressions is that we do not include a liquid in an equilibrium expression. That's because the concentration of a liquid is in fact a constant in itself. So we would just merely write the S2 minus divided by HS minus and OH minus. All right? And very quickly here, look at two more examples. The next one, we have KEQ is equal to concentration of the gold 3 plus ion times the concentration of the phosphate 3 minus ion, all divided by the concentration of AuPO4 solid plus H2O liquid, whoops, not plus, multiplied by, okay? Now, we just gave a rule. We do not include a liquid in an equilibrium expression. So it shouldn't be there. But also, we can't change the concentration of a solid. The concentration of a solid is a constant in itself. And so again, if we can't change it, there's no reason to show it in there because there's nothing we can do to it to affect this numeric value. And so therefore, we do not include a solid in an equilibrium expression. Now, in actuality, we're including them. And I shouldn't say that we're not including them. The actual way that we state it is that the concentration of a solid is considered as unity, as one. The concentration of a liquid is considered or defined as unity, as one. Well, of course, obviously, if we have this and this over 1, that ones don't mean anything as far as the numeric value. But it's important to remember this unity aspect when we look at this next expression, because if we were to write this quickly, KEQ would be equal to the concentration of HgBr2 solid divided by Hg2 plus ion times the Br minus ion squared because of the 2 in the equation. But I can't just say we're going to throw this away. Can't say we're just not going to include it because we would have an undefined mathematical equation at that point. We're saying that it is unity. So we would write that then as 1 over Hg2 plus times the Br minus quantity squared is the way we would do it. So we do have to define it as unity. All right. In our next lecture, we're going to go ahead and take a look then at some further applications of the equilibrium constant, which is a quantitative value, and take a look at how we can use that to make some calculations to tell how much product is present when a system has reached equilibrium. And we'll look a little bit further at Le Chatelier's principle.